Okay, so hey guys, how's it going? So today I'm going to be going through my video on fluence rate, energy fluence, and energy fluence rate. And in this video I'll be going through 8 problems. But today it's actually Christmas Eve, so Merry Christmas, Happy Holidays. And yeah, hopefully my nephews won't be disturbing me while I'm making this video, but no guarantees. But without further ado, let's begin. So typically in my videos, I tend to go through like formulas and definitions in the first couple problems, and then I generally try to increase with difficulty. Okay, so problem number 1. What are the formulas for calculating fluence rate, energy fluence, and energy fluence rate? And make sure to include the units. Okay, so now these quantities, it's important that you do have them memorized, and also memorize the units, include the units, because in many instances you're going to be putting these quantities within a formula. So in order to work out the unit analysis, you should know the units. So let's go through them. So first one's fluence. It's essentially dNE, which is the expectation value of the number of particles striking a finite spherical volume around point P, over dA. The units are meters to the -2, or they can be in centimeters to the -2. It's probably better actually to put them in centimeters to the -2. Like say for example, you want to calculate Kerma. Formula for Kerma is energy fluence multiplied by UTR over rho, which is in centimeters squared over grams. So in order to work out the unit analysis, you would want the energy fluence in centimeters to the -2. Fluence is denoted by the Greek letter phi. Fluence rate, that's essentially it's your fluence divided by dt, or time. Units of meters to -2 or centimeters to -2 multiplied by seconds to -1. It's denoted by lowercase phi. Energy fluence, it's essentially your fluence multiplied by your average energy. Be careful here though, because if it's a spectrum of energies, you are going to have to integrate with respect if it's a spectrum. It's in units of joules per meters to the -2, denoted by the Greek letter psi. And energy fluence rate, it's essentially your fluence rate multiplied by your average energy. Or it could also be your energy fluence divided by your time. Units joules, meters to the -2, seconds to the -1, lowercase psi. So one thing to watch out for here is that these quantities, they're defined by Greek letters. And these letters, they can look different depending on the font used. Particularly the fluence rate can look quite a bit different. Also the energy fluence rate, depending on the font that's used in whatever you're using, like your textbook, for example. Okay, so going on to problem 2. So this is a depiction of a radioactive source on polar coordinates. What's the value of the total solid angle? Okay, so the question is, what is the total solid angle? So essentially what it is this depiction denotes a radioactive source with a volume, and it's in polar coordinates. Beta revolves around the xy axis. It can go from 0 to 2 pi. Theta can go from pi to 0. The total solid angle is if you integrate over all the angles with respect to theta and beta. So essentially you're getting 360 degrees around this radioactive source. So why is this important? It's important because if you have a radioactive source with a volume that's decaying isotropically, it's not following a direct inverse square. If you're at a point over here, it follows the unit of solid, it follows the activity divided by the unit of solid angle times r squared. So that's where the inverse square is. Yeah, so what is the value of the total solid angle? If you integrate with respect to beta and theta for all angles, the answer is 4 pi. And I answered why it's important. Because if you have a source with a volume, you can determine the fluence at a distance. So if that wasn't clear enough, I'll do a quick example. So let's say you have a source with an activity, 6 times 10 to the 8 becquerel or centigrade per second, and the source is 0.5 meters away. What's the fluence rate? So fluence rate is equal to activity divided by 4 pi unit of solid angle r squared. This is your inverse square. So now we can substitute the values. Activity, 6 times 10 to the 8 centigrade per second over 4 pi, 0.5 meters squared. And we can calculate the fluence rate at that point, 0.5 meters away from the source. Answer is 1.91 times 10 to the 8 meters to the negative 2 seconds to the negative 1. Okay, so problem 3. Let's say we have a point source and it emits an equal amount of 1 MeV, 2 MeV, 3 MeV, and 4 MeV photons with a total fluence rate of 2 times 10 to the 8 centimeters to negative 2 seconds to negative 1 photons. What is calculate the energy fluence rate? And it gives us units of joules, meters to the negative 2 seconds to the negative 1. So notice here it's not a spectrum. It's an equal amount of these energies for the photons with the total fluence rate. So first thing we want to do is we want to calculate an average energy. Add them up, divided by 4. The answer is 2.5 MeV. We know that the energy fluence rate is equal to the average energy times the fluence rate. And we have the fluence rate. So essentially what we're going to be doing now is just a lot of unit analysis. So 2.5 MeV, average energy. We want it in joules, and we have MeV. So we're going to have to convert 1.602 times 10 to the negative 13 joules. And here we're going to throw in our fluence rate. And we're going to go ahead and, it was in centimeters squared. Let's go ahead and convert it to meters squared, because it says so in the answer. We get an answer of 0.8 joules, meters to the negative 2, times seconds to the negative 1. I think it's a pretty easy example, but still a very nice example. Okay, so problem 4. An X-ray field measured at a point P contains 8 times 10 to the 7 photons per centimeter squared per second per MeV. So this is going to be the energy fluence rate, but notice it's an MeV. So typically energy fluence rate would be in joules, unless they specifically ask for everything. With a uniformly distributed energy of 10 to 20 MeV. So what is the fluence rate at P? Okay, so we're going to have to create an integral to calculate the fluence rate. We have the energy fluence rate. So this is our distributed energy for our integral, 20 MeV over 10 MeV. And when we take the integral, we're left with E, and we can just sub in 20 MeV minus 10 MeV equals 10 MeV. Now we can cancel out for unit analysis, right? And so now we get 8 times 10 to the 8th. And now we're just going to perform unit analysis to convert it to meters, to the negative 2. We get our answer of 8 times 10 to the 12 photons per meter squared per second. Okay, now what is the fluence in 1 hour? So it's just a unit analysis. We're going to go ahead and convert the seconds. 2 hours. The answer is 2.88 times 10 to the 16 photons, meters to the negative 2 per hour. Okay, so problem 5. Let's say the same 10 MeV X-ray field is incident on 2 materials and measured at point A and point B. If material 1, if the kerma was measured as 1 gray, and the mu-TR over rho of material 1 is 0.0188 centimeters squared per gram, and they give us material 2 mu-TR over rho, which is 0.0162 centimeters squared per gram. So for part A, calculate the fluence at point A. So first you have to know the formula for calculating kerma, which is kerma is equal to energy fluence times mu-TR over rho. So we can sub in the value of 1 gray for kerma, which is also equal to 1 joule per kilogram. We could sub in our mu-TR over rho value. And we know that the energy was 10 MeV, so we can change the energy fluence. We can break it down into fluence times the energy. The energy is 10 MeV. Of course, there's quite a bit of unit analysis. So here's a 10 MeV. We're converting it to joules to match this 1 joule per kilogram. Here's our fluence that we are calculating. mu-TR over rho. Here's our conversion to kilograms, because 1 gray is equal to 1 joule per kilogram. And then here's our unit analysis for meters squared. So we can go ahead and calculate for fluence. We get 3.3 times 10 to the 14 meters to the negative 2. All right, so part B. So what kerma is measured at point B? So once again, we know the formula. We have the fluence now calculated. We can sub in the energy, which is 10 MeV, the fluence, and the mu-TR over rho of material 2 to calculate the kerma measured at point B. Once again, quite a bit of unit analysis. Lots and lots of unit analysis for most of these questions. Kerma measured is 0.86 gray for point B, material 2. Okay, so problem 6. If a radioactive source emits 10 to the 9 photons per second, each with a frequency of 2.7 times 10 to the 17 seconds to negative 1, calculate the energy fluence rate at a distance of 20 centimeters. Okay, so first we need to calculate the average energy. So if you remember from the formula, its energy is equal to Planck's constant times the frequency. You do not need to memorize Planck's constant. So let's perform that calculation. We get an answer of 1.12 times 10 to the 10 eV, but let's convert it to MeV because that's very common. So we get 1.12 times 10 to the 4 MeV. We'll go ahead and convert it to joules because energy fluence rate is often in joules. So let's go ahead and calculate the fluence rate now. So the formula fluence rate, notice that it says radioactive source. It does not, so you assume that it's a volume. Unless they specifically say point source. That's not a point source means it's not a volume. Radioactive source, assume it has a volume. So this is the formula. Activity over 4 pi r squared. So 10 to the 9 photons per second. 4 pi r, which is 20 centimeters squared. And then we're just going to go ahead and convert it to meters to negative 2. So now we have our average energy and our fluence rate. So we can just go ahead and multiply them. And we have our energy fluence rate now, which is 3.57 joules per meters to the -2 divided by seconds. Okay, so for problem 7, I have an example problem, and I'm actually going to show you how to work through it 2 ways. I'm going to show you a less, I'm going to say it's definitely less proper way is going to be the first method. This method right here, it's less proper. It's probably less correct, but it's to get you thinking with respect to like questions for the ABR Part 1 exam. Because you got to remember for the ABR Part 1 exam, you only get 3 minutes to answer, to calculate the question. And I mean, essentially, you're going to want to review your questions at the end. So my recommendation is 2 minutes and 20 seconds per question. So you want to be able to solve the questions very fast. So this first method is going to sort of put you in that kind of mentality. So let me show you. So problem 7. You've been exposed to a radioactive source that emits 10 to the 6 photons per second. You walk 5 meters at a velocity of 0.5 meters per second until you're away from the exposure. What was the overall fluence you were exposed to? So we know the formula for fluence rate. It's radioactive source, doesn't say point source, so it has a volume. We'll go ahead and put in the activity, 10 to the 6 photons per second, and the distance, which is 5 meters squared. We're going to calculate the fluence rate. We get our answer. 3.18 times 10 to the 3 meters to the -2 seconds to the -1. That's our answer for fluence rate. But it wants fluence. So we're going to have to get rid of seconds. So we're going to go ahead and multiply it by seconds to 0.5 meters, which is the velocity. And then we're going to go ahead and multiply it by meters to get rid of that. So we're getting rid of the seconds, we're getting rid of the meters, and we just have our total fluence. And we have our answer, 3.18 times 10 to the 4 meters to the -2. So essentially all we did here is we used unit analysis. Is it proper? Is it correct? Not so much, but and you have to really factor in speed for the ABR Part 1 exam. So now I'll work through the problem, but I'll work through it in a proper manner, in the most correct manner. The same question, though. So same question. You've been exposed to a radioactive source that emits 10 to the 6 photons per second. Walk 5 meters with velocity of 0.5 meters per second until you're away from the exposure. What was the overall fluence you're exposed to? Okay. Fluence rate is equal to dN over dt, 1 over 4 pi r squared. dN over dt is just activity, of course. Okay, fluence is equal to the integral of later time over the initial time. And this is fluence rate dt. And remember from physics that v, velocity, is equal to dx over dt. And I can rearrange this for dt to dx over v, right? I can just rearrange this. And now we're going to go ahead and substitute these terms into this formula. So fluence rate, we'll put this into there. dt, we're going to swap it for dx over v. And this is what we get. The integral is now x2 over x1. So let's sub in the quantities now that we have already. So activity, 10 to the 6 photons per second, 1 over 4 pi r squared, 1 over v, and then 5 meters to 0 is our x2 over x1. The integral of dx is just x. So you can put in 5 minus 0. Putting in the terms again, the quantities. And we get our real answer, 3.18 times 10 to the 4 meters to -2. Now, this is the most correct method. Are you going to do this on the ABR Part 1? Probably not. To do it in 2 minutes and 20 seconds would be quite a task. Okay, so this is problem 8. This is my last and final problem, but it's a very big problem. It's a very complex problem. In this problem, it actually comes directly from ADDX. I don't think I have my textbook on me. it's one of the main sources I use in my introduction. So to me, this problem, I remember when I first tried to work through it. I think I honestly, I think I worked through it for 8 hours or so, and I still did not get the correct answer. But I think what I was trying to do is I was trying to like make an approximation. But I'll show you the actual work through. It is actually a very, a difficult problem. If you're sitting down and you're trying to work through it on your own, like I was saying, I spent 8 hours and I don't think I got it right. I was trying to approximate it. But I'll show you the work through. So let's go ahead and go through it. Okay, and I got a little diagram. So a radioactive source emitting 10 to the 8 neutrons per second falls on a railroad platform 3 meters horizontally from a track. Now a train goes by at 60 miles per hour. What is the fluence of neutrons that strike a passenger at the same height as the source? And you can go ahead and ignore scatter and attenuation. So one of the trickiest parts here, is sort of how you're defining your coordinates for answering the problem and how you're going to set up your formulas. So in this case, the train is the y-axis. X-axis is the distance from the train and the source, which is 3 meters. And there is no height. They're saying it's at the same height. In this case, we can say, r squared is equal to x squared plus y squared. Okay, so just like we did in the last problem, we're going to go ahead and set up the formula for fluence. Same idea, we'll take the fluence rate formula, we'll plug it in there. We'll plug in dy over v for dt. Now what makes us different is that for r squared, it's equal to x squared plus y squared. So x squared plus y squared. So, when we look at the quantities given, we have the activity. We have 1 over 4 pi. We can take it out of the integral. We have the velocity, so we can take that out of the integral, 60 miles per hour. Now we're left with just that r squared essentially. Now it's with respect to dy, because we swapped dt for dy over v. And dt we swapped for dy over v. And we took out v, velocity. Now we just have dy. So now we're going to focus in on this integral. Okay, so focus in on this integral. It's actually a tricky integral. And notice that for dy, they're taking it from infinity to negative infinity. So I think how I initially tried to solve it is I assumed like an I didn't go from infinity to negative infinity. I think I assumed an approximation. I forget the exact values I used, but let's go ahead with this. Okay. So we're given x. In this case, it's 3 meters. So we can go ahead and sub that in. We'll square it, which is equal to 9. Now, we can calculate that y is equal to 3 tan theta. So y, tan is equal to opposite over adjacent, or tan theta is equal to opposite over adjacent. Tan theta, so it's equal to y over x, which is 3. They bring the 3 over to get the y. Now if I do take the derivative of this, it's equal to 3 secant squared theta d theta. And also I know that theta, I can rearrange this, right? Y over 3 inverse tan is equal to theta. I can rearrange this. So I have all those now. Okay, so let's kind of sub these in. dy, we know that. It's 3 secant squared theta d theta. So I'll go ahead and put that in for dy. Oops. And we know that y squared is going to equal 9 tan squared theta. And there's already a 9 there, so they bring the 9 out. There should be another bracket here. Now, there's a trig identity that says 1 plus tan squared theta is equal to secant squared theta. There's a trig identity for this. They reduce the 3 over the 9, bring that out. It's constant 1 over 3. And they throw in the trig identity, so this just equals to 1. So now they have a, what's the integral of d theta? It's just theta with respect to infinity and negative infinity and over 3. But we know that theta is equal to tan inverse negative 1 y over 3. So they go ahead and sub that in. Now, because it's from infinity to negative infinity, we're going to have to go ahead and take some limits. So that's what we're going to do with tan to the negative 1 y over 3. And we know that the limit of a tan to the negative 1 y over 3 is equal to pi over 2. And tan to the negative 1 y over 3 is, from negative infinity is equal to negative pi over 2. So the answer is, so they end up getting pi over 3. Because this is equal to pi, and this is 1 over 3. So we now know that the integral of 1 over x squared plus y squared dy is equal to pi over 3. So now we can go ahead and sub everything in and solve. So that's where we were before, subbing in the quantities. Now we can go ahead and sub in that pi over 3. So everything is the same. There's the pi over 3m. There's the velocity. And they convert it to miles to meters and hours to seconds. Gives us a final answer of 3.11 times 10 to the 5 neutrons per meter squared. Okay, so that's 8 problems on fluence rate, energy fluence, and energy fluence rate. I think I picked a lot of excellent problems. Of course, like usual, I tend to handpick the problems. I think that's almost about as good as it gets for those quantities. Also, in some of my other lectures, it allows like calculations where you're inputting some of those quantities. So I think you really are having your bases covered for those terms, working through these problems. So with that, I'd like to thank you for viewing, and happy holidays. Bye.